Hello and welcome to the wide world of physics. Today we're talking about something that we see a lot of. Not just the pen itself. The pen is actually just a vehicle for what we're talking about. It's the thing that's inside the pen. This one doesn't work anymore, which is why it's a good thing to take apart. But if you click a regular pen, it comes back because there's a spring inside of it. And if we take it apart, you can see that there is this very small little spring. Now, springs are everywhere and we can use them for a lot of different things. This one is for compression, this one is for tension, which means you pull it. The compression bit means you squeeze it. And it all comes down to a very simple concept, which is incredibly important to what we're going to talk about, which is the work of a man named Robert Hooke. Robert Hooke was an inventor, a mathematician, an architect, and he did a lot of work during around the same time as Newton. They did not get on, and by not get on, I mean Newton actually tried to erase Robert Hooke from history. The only paintings that we have of Robert Hooke are from descriptors of other people because Newton had them all destroyed. That said, Hooke was looking into how much tension you can put on a wire. This is just a regular piece of wire. How much tension could you put onto this thing before it stretched or broke? And he was doing this in his work as an architect. So, you can look at something like a slinky and see that if you stretch it, it wants to go back to its normal shape. That is the entire concept of what we're looking at, which is Hooke's law, about how much force that you can put onto something, and then it goes back to its original shape after you remove that force. And that is the key concept of what we're going to be talking about. So to prove Hooke's law, we need a very simple setup. I'm just using this clamp stand and bar just to hold the spring, basically, is all it needs to do. To do this, we need to understand that there are force pairs that are in operation, okay? We know that if you hang a mass onto the spring, the force of gravity will pull the spring downward. That's great. We understand that. We also understand that you have to have a secondary force pulling upward, which is the bar. The bar has to pull the spring upward. That's why you get the spring to stretch. That all comes down from one of Newton's laws, where force is mass times acceleration. So the force that is on this spring currently is due to one thing only, which is the acceleration due to gravity. So Hooke's work took that idea of force and mass and acceleration, in this case gravity, purely gravity, and came up with this concept that if you put a force onto a spring, it will stretch by a certain amount. If you double that force, it will stretch by twice as much. You can prove that very simply to yourself by effectively measuring it. If you look at a spring, measure it from a given point, and say this spring is 4 centimeters long when it's unloaded. So there's no force acting on it right now, it's just holding itself up. So if I add 30 grams, which isn't terribly much, onto this, we get an extension. So it's now, we go from 4 to 4.5. So we've gained half a centimeter. Not exactly a massive amount, admittedly. However, if we double that force, so we go from 30 to 40, 50, 60 grams, which is twice as much now. If we hang that mass on there, you can see it's extended a bit more. And we now have an extension of just over 5 centimeters. This all has to do with that entire principle of it being a linear proportion. It is directly proportional. It's a straight line. If you were to graph it, if you were to add more mass again, you would add more force, and therefore you would extend that line to be a nice straight line directly proportional to the force. Force and extension will be proportional. So now that we know that when you extend the spring, you can extend it by a proportional amount, and if you remove that force, it will go back to its original length. If, however, you extend that spring too far, you get past what is something called the elastic limit. When the elastic limit is exceeded, you've gone past it, you've put too much force on it, that spring is going to stretch out and never go back to its original length. Hooke came up with this idea. He was working with wires to do this. So if you stretched a wire or a cable or put something very heavy on it, like you're hanging a picture, or in this case what he was talking about was a bridge. If you put too much force on it, it's going to bend that cable so much it will stretch it to the point where it won't ever come back to its original length. So if you put too much force on it, you will go past the elastic limit. Now that's all proportional to something called the spring constant. So the spring constant on this spring here is one thing, but the spring that's in a pen will have a completely different spring constant, as will the spring in a car. So it's all dependent on how much force you need to withstand, how much your elastic limit needs to be, and how strong your spring has to be to go back to its original shape and not exceed the elastic limit. Thank you for watching. If you are enjoying these videos, please remember to like and subscribe below, and please continue to watch all the other videos on this channel.